Okay. So, as is traditional, I'm the last speaker of the conference. Welcome to the home stretch. Congratulations for making it all the way through. Well, not almost. So, I think we should all take a moment to thank the organizers who've done just an extraordinary job of organizing this conference and making everything work smoothly. I think there were 7 of them, so I'm not, but maybe Chen was their leader. So we should all give them a round of applause. Okay, so I first met Alex in 1981, in the fall of 1981, when he came to Columbia University as a visiting professor. So I was very impressed. I thought, wow, I was just past my PhD. And I kind of understood that he was young, but when I was asked to give a talk at his 60th birthday conference, I was really startled. How could this guy have done so much and accomplished so much and been a professor when I was just sort of new, and he was 60 years old? You've got a lot of time left, and yeah, you've just begun, I think. Yeah, so my mathematical contact with Alex is different from most of yours, I think. So I came to Columbia to study K-theory with Hyman, but I never really learned K-theory much. I wasn't much interested in, hadn't started being interested in automorphisms of free groups or mapping class groups, but Alex was there, and he was talking to Joan Berman, and he was also talking to anybody around, like even me, and he was telling me about this theorem that he had about automorphisms that have to fix the normal subgroups have to be inner, and then with Berman and her student McCarthy, he proved that solvable subgroups of the mapping class group are virtually abelian. So he was talking about all these things that sounded pretty interesting, and eventually I got interested. I saw him in several other occasions, but the next story I want to relate is about MSRI in 1989. I went there, and I had just fairly recently developed this space, outer space, and I told Alex about it, and Alex got very excited. He said, oh, we can prove that out of Fn doesn't have property T. So we heard that he doesn't like to waste time, and he got all excited because he thought he wouldn't have wasted his time coming to Berkeley because he would come out with a theorem. Well, we don't have a theorem yet, but maybe we'll do that someday. Right, so what I want to talk about today is, so this space, this outer space that we defined is space on which the group of outer automorphisms of a free group acts, and it's analogous to the symmetric space G mod K with an action of a lattice. And so today I want to explain some further development of that analogy. So we have out of Fn acting on, we have lattice in G acting on the symmetric space G mod K, and outer space is an analog of the symmetric space G mod K, except it's got an action of out of Fn instead of a lattice. Right. So, right. So I want to explain a little bit about this space and about further ways in which this space is analogous to the space of lattices. And actually, I had a plan. I was very well organized. I was going to put a picture on the black backboard. Maybe I'll put it over here. So the first example you learn about lattices acting on symmetric spaces is, of course, SL2Z acting on the upper half plane. So I'm going to draw the upper half plane over here, H2, and SL2Z acts. And the quotient is the modular surface, which, as everybody knows, looks like that. It's right. Kind of looks like a surface with two cone points and a cusp. So this is a nice space, a nice action. It's a proper action. Stabilizers are finite. If you want to, and this is the modular curve, people want to understand what this is and various properties of it, but many people are unhappy with this picture, basically because it's not compact. So in particular, algebraic geometers are unhappy with this picture because this is not a projective variety. So, and geometric group theorists are unhappy with this picture because they would like a space that's quasi-isometric to the group if they want to study the group, which means it has basically the same geometry. And to get that, you need a proper action with a compact quotient. So algebraic geometers, you can make this space compact in two ways. So you could either add a point to it, which makes algebraic geometers happy because it now becomes a projective variety. If you look upstairs, what happened is you added a point to the upper half plane at every rational point, including infinity, which is also a rational point. So that makes algebraic geometers happy, but it does not make geometric group theorists happy because you've changed, well, the action up here is no longer proper. The stabilizer of one of these points, like infinity, is the parabolic subgroup, which is infinite. So that's no good for a geometric group theorist. It also makes algebraic topologists unhappy because you might want to study algebraic topological properties of this group by studying this space, but you've changed the homotopy type of this space by adding a point. So instead of adding a point, you could instead think of adding a circle. So instead of adding just one point at infinity, you add upstairs, you're adding a point for every vertical ray going to infinity, so you're adding an entire line. Okay, now the parabolic subgroup acts on that line by translation, so the quotient is a circle, and you're happy. But of course, you have to do this equivariantly, so you have to add a line at every rational point. It's kind of hard to draw them. Okay? So this first compactification by a point is an example of what's called a Satake compactification. And this compactification by adding a circle is an example of what's called the Borel-Serre compactification. Actually, in this simple example, it was done much earlier than Borel and Serre. Borel and Serre generalized it vastly to lots of semi-simple algebraic groups. Right. So that's what. So downstairs you can call this a compactification. Upstairs you can't call this a compactification because if you just add the rational points or if you just add the rational lines, it doesn't matter. Space you have is not compact. Okay, so this is called the Borel-Serre Fortification. Yeah, I'm thinking about Borel-Serre as the one I'm interested in because I am a geometric group theorist. So this is called the Borel-Serre boardification. Board for border. So you added stuff to infinity. You've added stuff at infinity, and yeah. So what the features that this has is the action of my lattice on the boardification well, actually, there is an action. The action of this on G mod K extends to, and not only that, but the action is proper so after you add these lines, the stabilizers are now trivial. And so the action is proper and the quotient is compact. So if n is, so this is what happens for SL2. The picture is very simple and it's easier to understand. You added a circle at infinity. For n bigger than or equal to 2, for n bigger than 2, or actually equal to 2, well, instead of adding a single line for all of these parabolic subgroups, you add a Euclidean space for each parabolic subgroup. These Euclidean spaces, unlike in this case we just added lines, one-dimensional, and they don't intersect each other. They're completely disjoint. But in higher dimensions, these, well, as you know, parabolic subgroups intersect each other sometimes in smaller parabolic subgroups. And these intersect. And the pattern of intersection is given by the spherical Tits building. For G.
That's a Euclidean space for each standard parabolic. You fix a Borel or you don't?
For every parabolic you fix.
You
No.
fix a Borel.
No. I mean, it's like up here. So the standard parabolic here looks like that, right? But you get a line for every rational point. So there you have a Euclidean space for every parabolic. Okay? So that's the picture for, right. And the spherical Tits building has, you understand, so that means you understand the homotopy type of the boundary in particular by the Solomon-Tits theorem. The boundary of this boardification is homotopy equivalent to a wedge of spheres of some dimension, which is, yeah. Okay, so that's the picture in the symmetric spaces. So now we want to replace the symmetric space over here by outer space. And what I want to do is draw a similar picture. So I want a boardification here. So this is outer space, let's call it ON. So I want an ON bar, and I want the action to extend. And is proper and co-compact. Now for n equals 2, yeah, so I have to to tell you at some point what these spaces are, let me, instead of talking about, do I have an eraser? Oh, yeah. So instead of talking about general lattices and general groups, let me talk about SLNZ inside of SLNR. And the homogeneous space is, let me call it Qn equals SLNR mod SON. So there are many ways to think about this homogeneous space. You may think of it as a space of positive definite quadratic forms, normalized to, say, have volume 1. Or you may think of it as a space of marked lattices. Lambda in R to the n. So marked just means you don't just have a lattice, but you have a basis for the lattice. And modulo rotations. So modulo is some sort of isomorphism. Or another way you could think of it is a space of free actions of z to the n on r to the n. And I don't just want any free actions, because I don't want, for instance, z squared to act on a line freely. That's not a lattice. So what I want is that there aren't any invariant subspaces. So if you have an action with no invariant subspaces, that's called a minimal action. So you could think of this as a set of free minimal actions of z to the n on r to the n, modulo, of course, equivalence by rotation or flip by the orthogonal group. Okay, so then it makes it easy to say what outer space is. What's outer space? Well, z to the n acts on r to the n. What does a free group act on? Free group acts on a tree. Okay? I'm going to give my trees edge lengths, so I'm going to call those metric trees. So outer space ON is the space of free minimal actions of Fn on metric simplicial trees. Okay, so that's a complete definition of what outer space is. Maybe I shouldn't erase quite yet. So one way to think about this, so that's a fine definition, but it's a little bit hard to imagine. One way to think about this is if you have Fn acting on a tree, like everybody's favorite picture is.
What's the equivalence there? You had the equivalence under.
Yeah, it's just if there's an equivariant isometry between the trees. Yeah. So if I make A go this way and B go this way, it's the same as making A go this way and B go this way, because I can flip. Okay? So Fn acts on a tree, then the quotient is, this is everybody's, so here's, if I call this x, and maybe I make, let's see, ax go over here. Everybody likes to make bx go up here, but there's no reason you have to make bx go up there. You might make bx go over here. It still acts transitively on the vertices. So, whoops. Just trying to get colors here. So, if I take that edge, and look where they go down here, the green edge goes around one of these loops, and the red edge goes around two of those loops. So, given an action on a tree, I get what's called a marked graph. So what it is, it's a graph. And the generators of the free group descend to loops. You know, you look where the generator sends, pick some base point, look where the generator sends it, and then that gives you a loop for every generator down here in the graph. And so this marked graph actually gives you a homotopy equivalence, or it gives you an isomorphism of Fn with the fundamental group of the graph. So instead of marked lattices, you can, you could think of this as marked tori if you want, if you look at the quotient. And we have marked graphs here. Right. Okay, so that's a picture. Let me go back to my, Oh, yes, I also want to normalize. So these lattices are generally normalized, so they have volume 1. Let's make sure the normalize so that the quotient has volume 1. So here I've got 2 edges. The sum of the edge lengths is supposed to be 1. So that gives me a whole line of graphs. Okay, so in general, ON decomposes this outer space that I've just described. If you think about what happens in the quotient of the actions, the whole space decomposes as a union of open simplices So let me call this is a graph together with a marking. There's one simplex for every, well, there's a simplex containing this point, which I'll call sigma of GG. And how do I move around that simplex? I just vary the lengths of the edges, maintaining the sum is equal to 1. So if I have 3 edges, I get a triangle. If I have 2 edges, I get an edge, etc. So equals simplex of dimension equal to the number of edges of G minus 1. Okay? Now, for n equals 2, well, there's always a map from the outer automorphism of a free group to GLNZ, because any automorphism of a group induces an automorphism on the abelianization. For n equals 2, this is an isomorphism. And in fact, O2, well, can be thought of reduced. There's a slight technicality in here. O2 is actually homeomorphic to the symmetric space over here, which is H2. So let me show you back in our picture of the upper half plane what this decomposition into open simplices looks like. You're actually all familiar with it. This is just the Ferry triangulation of the upper half plane. So what are the simplices? Well, I've got what kind of simplices do I have? In this picture, in reduced outer space, the only 2 kind of graphs I can have look like that or that. So there's triangles and edges. So these triangles correspond to 3 vertex graphs. My my little rose over there corresponds to an edge. So it's a marked edge. How do I know that this marked graph is in the boundary of this? Well, if I blow up this middle thing, this middle edge, I get something that looks like that, and something that looks like that. If I collapse this picture, I get that picture. I could also collapse the other edges, though. If I collapse the other edges, I would get something that looks like that, or something that looks like that, with appropriate markings. So my whole picture, there's a triangle for every marked trivalent graph. There are edges for every marked rose. And this is the decomposition of my symmetric space. Okay? Right. So it turns out that, so I wanted to define a Fortification for this space. This was actually done by Vogtmann and Fnding. Imitated Borel-Serre, defined a Fortification with all the properties that you want. So why am I talking to you about this today? Well, let's look back at SLNZ or SL2Z. What I wanted to do in Borel-Serre was add a circle at infinity, but I could achieve exactly the same effect by just cutting off the cusp. There's a little circle that goes around the cusp. And in fact, this guy that I get, so upstairs, what am I doing? Well, I'm cutting off horoballs from my space. Okay, so Dan Grayson found a subcomplex or subspace of G mod K, which is homeomorphic to the Borel-Serre Fortification for G is SLNR. And I think he also did symplectic groups. So what are the advantages of doing this? So what we have is the interior of all these horoballs now, and we get something exactly homeomorphic to the Borel-Serre Fortification. All of these circles, all of these lines are now horospheres, so they're missing the point over there, so they're lines. So what's the advantage of Grayson's approach? Well, for one thing, it's a lot easier to understand than Borel and Serre's construction, and you don't have to work quite as hard. You already have a proper action. You don't have to prove the action extends if you know that you.
It's a gamma invariant.
It's gamma invariant. Yeah. So you don't have to prove the action extends, and you don't have to prove that the action's proper, because it's proper on the interior. Okay, so it makes many things much easier. So what I want to do today, I want to do the same for Vogtmann-Fnding Fortification. And it turns out what we'll get is something that's a lot easier to describe. And if we get there, I'll explain why you might, what Borel and Serre used this for, and what we would.
What did Grayson use?
The same thing. I mean, he got the same sort of a space, right? The point of looking at Grayson is that it's easier. And he gets the same results as Borel and Serre got.
Do you have to take a limit and let these circles go?
No, you're just cutting them off. You obviously don't want to cut too low, because then they'll intersect. As long as you're within the, Peter knows the right number, you'll these Horrorballs won't intersect. Okay? So, yeah. So I want to do the same for the Fnding Fortification. Yeah. Okay, so Besvina and Fnding did their construction one cell at a time. So I can drop the G from this notation. Remember, these guys I can drop the marking from my computation because it actually isn't going to apply to the construction. And so we have a cell sigma of G. And you want to add, instead of just a Euclidean space, you want to add a cell. So if we're just looking at one triangle, instead of adding a Euclidean line, we're just adding an interval. So you want to add a cell for each. So here we wanted to add a Euclidean space for every flag, for every parabolic subgroup, which is a stabilizer of a flag of subspaces. And so here we're going to add a cell for each flag of subgraphs. G contained in G1, contained in GK. But I don't want this to be trivial. I want to add, I want the rank to go down at each stage. So we'll call these core subgraphs. So that means they're proper subgraphs and no no separating edges. There's a technical constraint. Okay, so if you do that, let's take our rows like that. What's a flag of subgraphs? Well, there aren't too many. There's two of them. This contains, I guess I should give them colors. Well, I'll give them names instead of A, B. It contains A or contains B. So the simplex, here it is over here, sigma of G. And I was supposed to add a point at each end. One for this flag and one for this flag. Okay? So over here, yeah. My picture's getting too complicated. I'm adding points at all the rational points. On the other hand, I could also do this. I could get something homeomorphic by truncating. So if I truncated, I would get this point, and this point, this point, and that point, and that point, etc. So I get 2 points. You can think of those as the intersections of the points with the Horrorballs here. And the simplex, so yeah, when I add the extra points to the simplex, I get something sigma bar, which I'm going to call sigma bar of G, which is, whoops, right, this is not true. I better call it sigma hat of G. Sigma bar of G is when you add the points at infinity. Sigma hat of G is inside sigma of G. So this is why I'm saying I'm finding infinity inside outer space. I'm finding all the things that you have to add at infinity to get this Fortification, but I'm going to do it all inside of outer space. So anyway, that's the justification. Okay, now the next part. Right. So on each rose face, rose G. Let's look at the next case. 1, 2, 3, A, B, C. So what am I adding at infinity here? What am I, and how am I going to truncate that to get the same picture? Well, a flag consists of an ordering of A, B, and C, right? There are 6 flags. And no Americans in the audience. Okay, 6 flags.
Alan already went home. He's the only text.
Sorry? Yeah.
Alan already went home. He's the only text.
Yeah, okay. Right. There are 6 flags corresponding to the permutations of A, B, and C. So here is what the simplex for A, B, and C looks like. And I'm supposed to replace this by something with 6 vertices. Well, inside of this simplex, well, there's something with 6 vertices inside the simplex. If B is at first, you go towards the vertex B equals 1. And if C is next, you go left. If C is the next one's right, you go right. And what you get inside here is a permutahedron. So you can think of that as either blowing up all of these vertices into line segments, you get a hexagon, or you can think about it as truncating the simplex. You go farther in if you're in a smaller dimensional face. So for every rose face, I get a permutahedron. And here's now my description of the fortification. Sigma hat of G contained in sigma of G contained in sigma bar of G. This is Besvina-Fain's cell, which I haven't described for you. What's this one? This has, G has lots of rose faces. Put a permutahedron in each. And take the convex hull. So let me do that over here for you. I have, this triangle has 3 rose faces. In fact, all the faces are roses. I've put a permutahedron in each face. Permutahedra aren't so interesting for n equals 2, but they're still permutahedra. And now I'm going to take the convex hull and get a hexagon. So I'm going to replace that triangle by a cell. What I've done is truncated all this stuff at infinity. It, of course, gets more interesting with higher rank, but it gets pretty hard to draw. Let me just draw you one picture.
Yes, I missed something. What's the metric that you're using on your space?
I don't have a metric on it,
So I mean,
necessarily.
Convex, what are you, the geodesic?
Yeah, okay. So I'm in a simplex, right?
Okay.
Or, yeah, I'm in sigma of GG, which is a simplex.
Because like that, it seemed to me you were taking the hyperbolic. So you don't put a metric.
No, don't think of the hyperbolic metric. It's very misleading for outer space. In each cell is a simplex.
Okay.
So that's fine. I can think of it as a Euclidean simplex. So here's an example. Here's a graph. A, B, C,
So,
D.
there is no analog like in Teichmüller space. It's got all sorts of metrics.
There are metrics on outer space. That's a pretty different talk.
Okay.
The natural metrics on outer space are not symmetric. And in fact, you can prove that symmetric metrics, you can't make complete symmetric metrics except for incomplete ones. Yeah, right. Yeah. Yeah. That's a different story. There's lots of stories about outer space. Okay, so this graph has 4 edges, so it should correspond to a tetrahedron. Here's where A equals 1, let me see, B equals 1, C equals 1, and D equals 1, which means that all the other guys are 0. Right, what are the Rose faces? Well, if I collapse B to 0, I get a Rose. That's supposed to be in the face B equals 0. And if I collapse C to be 0, I get a Rose. So in each of these Rose faces, I'm supposed to have a hexagon, a permutahedron. So let me put those in. Okay, now I'm supposed to take the convex hull, and what I have and what I get looks like this. So it's a little jewel there, a little faceted jewel. And so I can also describe this as I want. It also has a description as truncating various edges, various faces. In this guy, I've truncated the bottom and the back, the top and the front side, and the line here and the back line. So, theorem. And this is joint with Cauve-Books. This sigma hat of GG. So this convex hull is called sigma hat of G is homomorphic to Besvina and Fane's guy sigma tilde of G, sigma bar of G. So the cells are actually homomorphic. And this actually answers an open question. Of Besvina and Fane. Their construction was a little more difficult, shall we say. They couldn't even tell whether their cells were actually cells, except by appealing to the Poincare conjecture. We've got a simplex and we truncated some sides, okay? So these are cells. Okay? So, right. Now, I have 5 minutes left to tell you an application. Right. So what did Borel and Serre use this Fortification for? Well, they used it to prove that G mod K bar, to prove that the lattice is a virtual duality group. In other words, there's an isomorphism between, gamma, if gamma is in torsion-free finite index, then the cohomology of gamma with any coefficient module m is isomorphic to the homology in a complementary degree of gamma. And you can't just put M here because it's not a Poincare duality group, but you have to tensor with a module D, which turns out to be the cohomology. D is the cohomology. Yeah, I don't have room for this, but I have a whole nother board. Oh, yeah. D is the cohomology of gamma with coefficients in Z gamma. If you have a proper action, proper co-compact action on a space, like we now do, you can identify this with the cohomology with compact supports of our space. Right. Okay, and it turns out that this works, yeah. Right. In order for this, in order to get a virtual duality group, you need this cohomology to have a certain form. You need this cohomology to vanish in all but one dimension. Okay, so yeah. I guess I'm just going to have to ask you to imagine that having a simple description of the space makes it easier to calculate the cohomology with compact supports. Let me just give you a completely uninformative idea of the proof. Let's just say to prove, so if you want to prove that this cohomology vanishes, in particular you want to prove that the space is highly connected at infinity. So what do? You have this space, On bar. On bar, turns out, is contractible. So it doesn't have any homology at all, but that's not the homology we're interested in. We're interested in the cohomology at infinity.
Excuse me, are you proving a similar theorem for the automorphism group of the free group?
Yes.
So the theorem is the same theorem?
Theorem is the same theorem. Yeah, same is true. I'm running out of time, so.
I just want to know what the
statement
is, how you make it.
So the statement is that
You had the theorem here for a lattice, and
right.
on the left it's an exact.
Yeah. So here the theorem for a lattice, this should have been G mod K bar, and the theorem is still true if you use On bar. So the theorem is still true that out of Fn is a virtual duality group. Okay. So On bar is contractible. So here's On bar. If I've got a compact set K, what does it mean to prove that it's highly connected at infinity? It means if I have a map of a circle into the space that lands outside of K, then I want to prove that I can contract it. I can fill it in with a disk that still lies outside of K. That's the easiest way to prove something's true. Well, since the space is contractible, I know I can fill it in by a disk. The problem is the disk might enter K. So the 1-minute version is I define a Morse function on On bar. This happens to be a combinatorial Morse function. So I look at a point V where f of V is minimal. And I look at the SK surrounding V. That maps here into some place that's bigger than V. And I prove that the upper link of this point is highly connected, so I can fill that in by a disk. I don't know if you're following this, it's fast. But the Morse function allows me to push my disk a little bit farther out of my compact set. And I can continue doing this until I actually get in the compact set. So the ingredients I need are this Morse function, which depends on Chiswell and Perry's theory of length functions on groups, and and some combinatorics, which I haven't got time to enter. But we're all tired, so.
Thank you, Karen, for